So in our last class, we had discussed uh, the lower bound theorem. That means how to find the lower bounds of different algorithm and what is the necessity of this. Okay. So today we will discuss another kind of analysis of algorithms that is known as amortized analysis. So actually, in uh, uh, in a you can think that amortized analysis is an average time analysis, but this is not average case time complexity. Please be careful about these two. Amortized analysis gives us the average time analysis, which is different than average case time complexity. In average case time complexity, actually the probability of the events are related, but in average time required for every operation. What is the average time required for or by every operation in a set of n number of different data structured operations is the amortized analysis. So what is amortized analysis? This analysis finds the average time required for each and every operator in a set of n number of data structure operations. Okay. So if there are n number of operations if there are n number of operations, then what is the average time of execution or analysis for each operation is known as amortized analysis. Okay. So which is completely different than average case time complexity. Okay. So why we require this, I will give some examples, then I think it will be clear. But before that, again, please don't get confused between these two. Average time analysis by each and every operation is amortized analysis, and average case time complexity means it is depending upon the nature of the input, that how when we are sending some random inputs, how the algorithm behaves. Okay. So these two are the different topics. Next, actually amortized algorithm gives us, already I have told, that suppose we are having a sequence of n operations. Let we are having a sequence of n operations that take worst case time complexity t of n. Okay, let we are having an algorithm where there are n different operations and the time complexity of these n operations is Tn. Then what we can say, the amortized cost per operation is equals to Tn by n. Now I think this is clear to you. If there are n operations and the time complexity of the algorithm is Tn, then we can say that the amortized cost per operation, that is for each operation, is Tn by n. Okay. This is not average case time complexity. This is amortized cost or amortized analysis of each and every statement. Okay. Let me give one example. That suppose we want to perform some stack operations. Okay. So we know that there are two stack operations, major two or famous two stack operations. One is push, another is pop. So in push we push an element onto the stack, and pop we pop an element from the top of the what stack, right? So here we know that since this is an assignment statement, therefore time taken to execute this is big O of 1. Similarly, to pop an element from the top of the stack is also an assignment statement. Therefore, we can write that the amortized analysis or amortized cost of push and pop is big O of 1, which is constant, we can say, or in another term, let the cost of operation is only 1. Okay, so this is 1 and this is 1. Instead of big O of 1, we can write 1 only. There is no problem. Now, if there are n such operations, then what will happen? If there are n operations, combination of push and pop, then we can say that the time complexity is theta of n. Okay. Now think about an operation, say multi-pop. Okay, multi-pop S K. So what is the meaning of this multi-pop K, or what is this operation? It will pop out K number of elements. Listen it very carefully. It will pop K number of elements from the top of the stack if K if K is less equals to n. Hope you have understood. That means multi-pop is an operation which will pop out K number of elements from the top of the stack if K is less equals to n. So if K is greater than n, then we can say that stack is empty. Stack is empty. Right? So, but if K is less than n, multi-pop Sk will pop out K number of elements from the stack S. Clear? Then what will be the time complexity of the multi-pop? Think about this. We are having a multi-pop S, K, and we can write this algorithm as while stack empty S is false and K greater than 0. That means at least we want to pop one element. Okay. What we can write? 2, immediately we will pop from the top of the stack and we will decrement K equals to K minus 1. So multi-pop, pop out K number of elements in this way. Pop S, K equals to K minus 1. What is the running time? That is the question. Now, what we are getting from here, this multi-pop operation, single operation, think about it is a standalone operation. Let us consider this multi-pop is a standalone operation, and if we find the time complexity of this multi-pop, then what we will get? It will be minimum of either S, that is total number of elements onto the stack, okay, or K. We can also write the n. There is no problem. We are considering S is the total number of elements in the stack at that time, okay, and K is the number of elements that we want to pop out. So the operations is Sk. So if K is less than, if K is less than n, K is equals to less than n, then what we can pop all the K elements. But if K is greater than n, then there may be S number of elements on the stack. Okay. If K is less than n, and if we want to pop out all the elements, then there is no problem. We are popping out n number of elements. But if K is greater than n and there are S number of elements, then we can only pop out S number of elements. So the time complexity of this algorithm is minimum of number of elements present in the list, or k, whichever is minimum. Okay, so then suppose we are writing this algorithm for I equals to 1 to n multipop sk. What will be the time complexity? So here this k may be order of n, because at most the stack can be full, okay, and we want to pop all the elements. So if there are n number of elements on the stack and we want to pop out all the elements, then the order of the multipop is n. If we have the stack full and we want to pop out all the elements, then the time complexity of multipop is big O of n. Now, if we perform n number of operations for this multipop, what will be the time complexity? N into order of n. So that is equals to order of n square. So what we can say, the multipop operations, if an algorithm contains multipop operations for n elements, then the time complexity is order of n square. Okay, right? Which is correct. Obviously this is correct, but this is not a tight bound. There is a fallacy. Just you consider, think about that, there are n number of elements for I equals to n. We want to perform n multipop operations, and each multipop operation consider big O of n time complexity. Then for n number of elements we require big O of n square. This is very much correct, but this is not the tight bound. Why? Because see, when we do the multipop operation, if there are some elements onto the stack, then only, okay. So for any multipop operations we need push operation. So if there are n number of or if the size of the stack is n, so how many push operations we can do? At most n, not more than n. So if the size of the stack is n, then we can perform n number of push operations at most. Okay. Then how many times this multipop will operate? Multipop sk, at most n, not more than that. So therefore, though the standalone multipop operations is showing that it can take big O of n square time complexity, but this multipop operations is depending on the push operation, and if there are not if there will be at most n number of push operations, and this multipop will pop out at most n number of elements from the stack, not more than that. Therefore, though the loose upper bound is saying that the time complexity of multipop is big O of n square, but the actually right complexity is order of n. Therefore, big O of n by n, that is equals to big O of 1, is the amortized cost of multipop. Okay. So I think you have understood. If you have any doubt at the end of the class, you can ask. I don't have any problem. Okay. So sometimes it may seem to us that the time complexity is much bigger, but if we go for finding the average of each operation, then we can find that this is lower than this. So here in this case we can say this is loose upper bound, and this one is the tight upper bound, and we can say that the average cost or the amortized cost of each operation is this. Okay. So let us go for another example. I think then it may be a little bit clear more. Okay. Let we want to design a k-bit counter. we want to write an algorithm for a k bit counter. Okay, so we are considering an array from 0 to k minus 1. Let initially and all initially x is 0, x is the value that we want to find, and therefore all ai is equals to 0. If we start with the counter 0, then all I equals to 0. Then for each, or for I equals to 0 to k minus 1, what we will do? We will add 1, that is modulo 1, with the previous sequence, nothing else. So what we will add? We will add 1 mod 2 to the power k, that is we have considered k number of bits. We are designing k counter, k bit counter. So we have to add 1 with the previous. So how we can write the algorithm? We can write that increment a, let I equals to 0, initialization, then while I is less than a dot length, obviously k here, and ai is equals to 1. Okay, then what we do? ai is equals to 0. Number 4, we will increment this counter I equals to I plus 1. Then 5, if outside of the loop, if I is less than a dot length, then ai is equals to 1. I am giving you one example. Let us design a k bit counter. Here we are considering 8 bit counter. Okay, so what we will do? Let the counter value is we are writing here, and let a 0 to 7 and total cost. Okay, here we are writing total cost. So cost means number of bit flipped or changed. Okay, here cost means we are flipping the bits, nothing else. Here you check, if ai is less than a length and ai equals to 1, we are flipping ai is equals to 0. Otherwise here ai equals to 1. So we will just flip the bits. So let counter is equals to 0. Therefore we know 1, 2, 3, 4, 5, 6, 7, 8. So this bit is 0. Here you check, while I is less than length and ai equals to 1, no, ai is not equals to 1. Therefore we will go out of the loop, and if I, yes, 1 is less than length 8, ai equals to 1. So in the next, what we will do? We will increase the counter by 1, 2, 3, 4, 5, 6, 7. 1, a1 is equals to 1. Okay. You consider from this side 0. This is not. This is 0. 1, 2, 3, 4, 5, 6, 7. So we are changing a0 is equals to 1. So initially the cost was 0. We have flipped 1 bit. So the cost of this operation is 1. Then 2. We want to make this counter 1 to 2. So 2 means this one will be 1, this is 0, and all others 1, 2, 3, 4, 5, 6. So 4, 4, 8. What is the cost? How many we have changed? We have changed this 1 to 0 and this 0 to 1. So 2. Okay. So 2 plus 1, total cost is 3 now. Got the point? So here previously it was 1 and now we are getting 2. So the total cost of this up to this operation is equals to 3. Then if we increase the counter to 3, then what we will get? 1, 2, 3, 4, 5, 6, 1, 1. So we are changing 1 bit. So that is 1. So this is 4. Similarly, you can go for 4, 5, 6, 7, 8. Okay. So what we'll get, this is if we go on 8 bit, so it will be up to 16, 9, 10, 11, 12 up to this. So next, if we go for doing this for 4, what we'll get? 1, 2, 3, 4, 5, 1, 0, 0. Okay. So this is the cost for, we are incrementing this one, and the total cost will be equals to 4. Here you see we have changed 1 bit, 2 bit, 3 bit. So total cost is 3 plus 4, 7. Similarly for the next we will get 101, all others are same, so 8. For 6 we get 1, 1, 0, so this will 10. Then 1, 1, 1, 11. Then 1, 0, 0, 0, this is 15. Okay, so this is the total cost we are taking. If we go on analyzing this, if we go on finding the time complexity of this algorithm, what we will get? Here there are at most k number of elements. Okay, so k times, in worst case it will execute for k times, right? And if we change, if we execute this for n number of times, then the time complexity will be equals to theta of n into k. Why? Because a single execution of increment, if we increment this for a single time, then it will take k times, and if we apply, that is for I equals to 1 to n, if we implement this k bit counter, the time complexity will be theta of nk. But we will show that no, this will not be theta of nk, only theta of 1 will be the time complexity of each k bit counter operations. How? So first let us analyze the operations that is going on here. Okay, without going to the only for the algorithm, let us check that how these operations is going on or operations are going on. Think about this. Just a minute. Here, how many flips we are doing? 1. Next, we are adding 2. Then in next, again 1. Then in next, we are adding 3. Then 1. Then we are adding 2. So there are a relationship, or there is a relationship between the increment of the cost, because the number of flips is depending upon the number of 1 or 0 in the bit. Okay, just think in this way. How many times this A0 bit flips? This is the A0 bit. How many times it flips? You see, each alternate change we are flipping this. So 0, 1 change, again 1, 0 change, again 0, 1 change, again 1, 0 change. So every time it is being changed. So we can say that whenever we are calling the increment function or the algorithm, this changes. Okay, for each call of increment, A0 changes. Now how many times A1 changes? You see, every other times it is changing. You see, these two are 0, 0. These two are 1, 1. So no change. Again, it changes 1 to 0. Then again no change. Then change. So every alternate time it changes. So A1 flips n minus 2 times. If we call n number of increments, then A1 flips n by 2 times. Similarly, A2 flips, check. A2 for 4 number of operations, this is same. So after 4 iterations, it will change and it will exist for 4 times, then again it will change. So A2 flips for n by 4 times, though apparently it looks like that whenever we are calling the increment function, it will change. All the bits k will change, but no, this is not correct. So A0 changes each time, A1 changes n by 2 times, A2 changes n by 4 times, and so on. So we can write, in general, any bit AI flips for n by 2 to the power I times, okay, n by all are floor value. Check this. When I equals to 0, 2 to the power I, 1, so this is n. Every time it changes, n times it changes. I equals to 1, this is n by 2. I equals to 2, this is n by 4, and so on. So a bit AI flips for n by 2 to the power I minus of, 2 to the power I times. Not every time all the bit flips. Clear? Right? So I am erasing this. I think this is clear, that a bit AI for n call to increment AI flips for n by 2 to the power I times, not every time. Okay. So what we can write, total number of flips, which is cost, total number of flips or cost in this case, in the sequence, that is, if we call n number of sequence of this increment operator, then we can write the total cost is equal to n by 2 to the power I floor value, and this I is equals to 0 to k minus 1. Okay. Now we can write that this is I equals to, this is I equals to 0 to infinity. We can add few more values here. Okay, n by 2 to the power I to I, therefore we can write n sum of 1 by 2 to the power I equals to 0 to infinity, and that is equals to 2n. So we know this value is 1 by 1 minus half. Okay, this sum is equals to 1 by 1 minus half, and we will get this equals to 2. So this is 2n. Now see, the total cost for n number of increments calling is equals to 2n. And how many operations are there? N number of. So what is the total cost? So we can say that this is equivalent to big O of n, and since there are n number of operations, therefore the cost for each operation is equals to big O of 1. So we can say that the amortized cost per operations of increment is equals to big O of 1. So though sometimes it looks like that the time complexity is higher, but it may not be the actual cost. So in this method we can find the average time taken by each and every operation. The method that we have followed is known as aggregate analysis. Okay, aggregate analysis. The method that we have followed to find the amortized cost is known as aggregate analysis. We have another two different kind of analysis for amortized analysis. One is accounting method. So first one is aggregate method, next one is accounting method, third one is potential method. Okay. So these two we will discuss in our later classes. Clear? So for today, this is I have to stop. From the next class, again we will discuss the accounting method and the potential method. If you have any doubt, please ask, because all of these are very conceptual things, so you may have some doubt. Therefore, if you have any